Okay, so hey, I'm Fabian from the ISB CGC, and we're going to be kind of demoing what we've been sort of working on recently. We're trying to focus mostly on data discovery and data access, trying to make that easy for researchers, and specifically some of the more downstream omics derived data. And so I'll have a use case demo. We also have the documents for this. There's some queries for BigQuery, and then a notebook, an R notebook that we're going to be using. And those are available in the documents shared via the main document. And we also have a nice little PDF outline sort of that you can follow along to go through. So the outline is going to be how to find tables of interest in BigQuery, specifically, using the table search UI that Kotha presented on. Then how to conduct, sort of exploratory data analysis using BigQuery. And this includes a little bit of cohort building and just investigating the parameters of your data, sort of the ranges and stuff. And then we're going to jump straight into an AI platform notebook, which is going to use one of the BigQuery SQL searches that we have to kind of move along into the more nitty-gritty data analysis, the downstream stuff. So we kind of would like you to follow along. It's kind of tough with this remote, but you can kind of run all the analysis that we have in this just from a Google, as long as you have a Google account for the BigQuery, and then in any type of notebook that you want. Google Colab is a pretty easy one. It's free, easy to set up and easy to run things on. The Google Cloud has a Jupyter notebook set up now that I think some other presenters also were using earlier. You can run this from your home console if you want, if you have an R window that you can pop open. You do need credentials to log in to kind of do the query. And if you have any trouble with that, just email us. We're always here to help. And we can set you up in our project if you want to run these trial analyses after we've done it. And you can also demo some of your own maybe trial stuff for 3 days. So yeah, to get started, I guess, jump into this ISB CGC link. I have it open here too. So this is our homepage. Via this sign in here, you can access the cohort builder and some other stuff, and the middleman database that we talked about yesterday as well is here in a couple of community notebooks, but we're going to be starting on the BigQuery table search. So this is a new UI that we've built, which lets you kind of preview all the tables that we have in BigQuery, which is 300 currently open access. We're also starting to populate it with closed access, and those are going to be gated behind the sign-in button using the OAuth stuff. So you can preview a table, shows you the parameter, shows you the schema, and then you can also see some of the lines. And so here you can kind of get a picture of what the actual data looks like. So not just, this is a string or something, but you can also see the extent of the range of the data. So we have some filters, and today we are going to be working with TCGA. We also have this source and data type. And so for this demo, we decided to combine some clinical data along with some RNA expression data, gene expression, and also some protein expression here. So yeah, you can jump into the clinical table, same as before, and preview it as well. And the main component that we're going to be using here is the case barcode, which is kind of our unit of samples. We're going to be looking at the disease code, project short name. It's kind of a bit of redundant information, but we also have a bunch of clinical data like days to death, days to birth, and then days to at diagnosis, or age of diagnosis is another one here. So yeah, once we've kind of decided on the tables that we want to use using this interface, we have a nice little button where we can jump straight to BigQuery, either here or here. And we have a little bit of a warning, just letting users know how to proceed or what to expect when they get to the Google Cloud platform. So this pops open a new tab, and we're directly on the Google Cloud console. And so here it's the same table that we kind of were looking at just now. Once again, you can get the details, number of rows, 11,000, And you can also get a preview of the table, same as before. So I've prepared a couple, in general, this is like kind of the workspace that users are gonna be on. If you click up here in the navigation menu, you can access VMs where you can run any type of pipeline that you want, as long as it's command line interface. You can run Python, you can run R in these VMs, and you can kind of scale depending on what you need. Then there's access to the Google storage buckets, and then this AI platform, which we're going to be using later on, which has some nice notebooks. This is a relatively new feature, but I've been kind of, I'm a big fan of it. But we're going to be doing the BigQuery for now. So I've prepared a couple of queries already, and this is just pretty much standard SQL. So we're going to be querying the clinical table just to kind of get an idea of the data sets that are in there. And so these queries run pretty much instantly now because I've been prepping them, because I've been running them while I was prepping for this. In general, this is between 5 and 30 seconds. Some of the more complicated ones took about 30 seconds to run. Most of it will be instant now, considering Google caches them so that when you rerun them, you don't have to repay or anything like that. But this first query was just looking at distinct project names and then the count of the case barcode. So basically this is how many cases do each of these projects have and what are the projects. So it's a really easy, quick way to sort of get a picture of what the data actually look like. And so this condensed, I think is 11,000 rows. And we can see that, breast invasive carcinoma has about 100 cases, but we kind of decided for this demo to focus on the kidney cancer. So we have this, this KIRP and KRC, which is kidney renal papillary cell, and then kidney renal clear cell carcinoma. So 537 cases and 291. So I have a secondary query here, which gets some information about the cancer types. So it's also pretty quick. I think when I first ran this, it was, this actually wasn't cached. So it took 0.4 seconds to run, really quick. So we're getting the information again of the number of cases. And then I've also included minimum age and maximum age just to get an idea of the extent of the data. So they look pretty comparable to me. And we can also do, if you're more interested, if you have a more complicated cohort that you're looking for, you can do subsetting. So in this case, I'm limiting age diagnosis to less than or equal to 80 and greater than or equal to 30. And that kind of dropped a couple of the cases out. I mean, you can do whatever you kind of want here. There's a whole bunch of different parameters that you can kind of use to create a cohort. And you can even get some initial sort of ideas of what your data will end up looking like. So then we are going to swap over, this is the clinical data, it's in one table. And then there's also expression data, both RNA-seq and protein expression data that are associated with these clinical data. They live in this TCGA HT38. So if I go here and I click on RNA-seq gene expression, and I look at details, so this is a table with 600 million rows. It's a huge table, contains a whole bunch of gene expression data for every gene that was assayed and every case. So it's a very big data set. You probably wouldn't be able to load this into R easily. I personally have never loaded any data set, data set with this many rows into R. Python could probably handle it. But in general, you're going to run into some execution issues with the size of this data. So what I'm doing here is I'm determining the number of cases with expression data in this RNA-seq gene expression that match the cancer types that we care about. So we have a wildcard character here to allow both Kirk and Kirk. And I'm grouping them by the project short name. And so we see the same thing, 530 cases and 289. And so that's kind of nice to double check because, there are definitely instances where a case might be reported in the clinical data, but then it doesn't have the matching gene expression measurements because, as these pipelines or as these workflows kind of advance through it, sometimes you lose data at one point or another. So what we can also do is maybe look at how many genes are there per gene type in the table, because there's a whole bunch of different gene types, obviously. Protein coding expression, there's no RNAs, long non-codings, all that kind of stuff. And so the ones we kind of care about for this demo is protein coding. So it's 19,712 genes have at least one measurement in this table, which is, you know, pretty close to the max, I guess, for humans is 20-something thousand. And then we have also, you know, a query to determine the number of genes measured per case in protein coding, or the protein abundance measurement. So this is basically the same query, but I'm running it on the protein data. And so I'm ordering this by case barcode. And here it's a little bit, there's fewer, not as many proteins were assayed for abundance as genes were for expression. So generally it's about 194, some of them have 183, and we'll probably have to end up using sort of the minimum amount to make sure that all our data, all the cases that we're interested in all have the same data so that our comparison is maximally interesting. And then finally, we wrote this very long join. And so what this join does is it pulls down the RNA gene expression for all patients that are in either the KERP or the KERK project. And then it pulls down all the protein expression and then performs an inner join. And so what that means is it takes all the gene expression data and all the protein expression data, and for every gene where there is information for every case, it will join them and it'll drop all the ones where they don't. And so kind of the workflow here is you have to write these individual sort of queries of what you're interested in. And I'm also taking the average of the protein expression and of the FPKM values. So sometimes there are instances where a single case might have multiple aliquots and therefore multiple gene expression measurements. I'm not sure if average is really necessarily always the best thing to do. Depends on your data type, but you know, we kind of trust researchers to determine what they find important and sort of whether or not they think that this is, you know, we trust researchers to sort of design their own analysis flows. But for the sakes of the demo, we're just going to take averages to make sure that we have one value for a gene and one value for RNA expression and one value for protein expression. Because as soon as you have multiple values, you get a combinatorial sort of explosion for the join data table. So it's kind of important that we have a single value associated with each of these. So I'm gonna plug this large query in here. It can take up to 30 seconds to run sometimes. When we were designing this demo, we also tried to kind of perform this join in R. So we put in the protein expression and the gene expression as two separate queries, loaded that data into R, and then figured we could join from there. But it took about 20 minutes to download the data from the BigQuery into that R session because it was so much. I mean, even though both of these were on the cloud, there's still significant transfer speeds associated with getting that much data. But considering when we've done this query, it's kind of limited by the number of protein abundance values. So it cuts down pretty heavily on the number of genes. And BigQuery is really good at performing these complex operations in a really short amount of time. So this query took 5 seconds. I mean, it's really nothing in the grand scheme of things. And then we can use this to jump into a Jupyter notebook. So I'm going to be pulling up this pipeline or this notebook. And so this is just like a general demonstration too of how versatile, I guess, the Google Cloud Platform is for researchers, for scientists. So you can boot up a new instance, you can do R or Python, and you can even customize the instance with different amounts of networking power and disk space. I already have one open though, so I'm gonna just jump into this one. And so we took this query, let's open up a new notebook, and then we kind of imported it into an R session here. So it's just, this is a straight copy and paste from the other one. So we have to install a couple of packages. It goes pretty quick. And then oops, we have initial query. This is similar to the one we ran earlier, just kind of building our cohort. And here we have this now in the data table, data frame. And we can do some very initial quick level plots just to compare age distribution. We have a lot less data for KERP than we do for KERK. That's expected, kind of matches what we saw earlier. And then we're going to import our big joined table, which is DNA expression and protein abundance at the same time. So we process 36 gigs, happens pretty quickly, relatively speaking. You have to wait a little bit. Are there any questions while we wait? Okay. So we have a header for our table here. We have gene expression, and we have protein abundance here. And then we have, project short name, either KERK or KERP. And then we have each of the case barcodes, which are sort of our unique identifiers. So we can, just to double check how many cases we have 214 and 472 cases for each of these. And then I have to do a little bit of a transform here to go from this format into a more, a friendlier format to interact with R. So what I'm doing here is I'm grabbing the gene expression for each case, and I'm making a table which has one column, which is gene name, and then a column which corresponds to each of our cases, marked with the cancer type that they're coming from as well. I have to do the same transformation for our protein abundance. Not have to, but I want to. So we have the same here. This is protein abundance now. And then we can separate the cohorts by column names. And we can generate a nice little scatter plot, which is comparing the gene expression values between the KERK and the KERP cohorts. And so gene expression looks pretty similar between the two different cohorts, between the two different cancer types. Protein expression does not, or protein abundance doesn't look quite as clean as somewhat to be expected, I think, given just the standard biology underlying this. And then the other nice thing that we can do is, so, this is just an R session. You can, every researcher, every biological researcher is pretty comfortable, I feel like, with R almost nowadays. So you can boot up a Pandas or a Python notebook as well. You can use whatever analysis tools you want. And if you have other data analysis pipelines you have to run, sort of the more nitty-gritty alignment stuff, you can always boot up a VM in the Google Cloud Platform as well. But you can load all these bioconductor packages as well. One of the cool ones here is math tools, which looks at variance between two different cohorts. We can use BigQuery once again to access the math tools. So we have two different queries here, accessing the variant information. And we can just load them into data frames using this query exec. And then we have to do one quick little transform because there's some issues with the column names. But if you're familiar with the data, you can figure that out, or we can always help too if anybody runs into issues. And then we have, access to a whole suite of plotting tools. So this math tools one is really cool. It does a comparison, so we can kind of tell this KERK has a single case with over 1,000 mutations, which is kind of interesting to see. Overall, the profiles of mutations between these two cohorts don't really look all too different, which kind of also matches the expression data results we got earlier. And then we also can do an oncoplot, which kind of shows you which mutations are kind of shared between all the different cases. And so here again, it seems to be this one case is kind of a bit of an outlier. But so yeah, there's a big range of analysis you can do. And I think that the one thing that we're really trying to emphasize here, or the one thing that we're really trying to provide to users, is the ability to interrogate data sets and determine sort of what data sets are useful for their research cases and really provide the tools for them to be able to very quickly and rapidly sort of assess the quality of data that they have in front of them and how they, make it easier for them to join data sets across different data types and make it easy for them to run whichever analysis that they want to run.
Are you planning on making the kind of analysis scripts that you're showing on the right side of your screen available in general?
Yes. So I have those we have those in the ISB,
I guess I'm asking as like a resource to users, not for.
Yeah, I mean, we have a lot of those types of things in our community notebooks, actually. So we have community notebooks here. This is our docs page, and we have a whole bunch of these little sort of tutorials and ways to use BigQuery to do data analysis available here. And we generally try to keep it have both Python and R. Does that answer the question?
That's exactly what I was.
Yeah, and I mean we're also always available for contact. We do a lot of one-on-ones with researchers too, if they have any problems with it or if they want to do an analysis and they're kind of struggling with it, maybe we do one-on-one sessions as well.
How does that one-on-one support work? Is that just for people that are funded by NCI, or
so we provide? It's pretty much for everybody, honestly. We also provide $300 of cloud credits to any researchers that wants it. And then there's always the Google free tier as well, which will let you do a terabyte of queries for free, boot up a micro instance as well. And that's, as far as I'm aware, is never going away. So there's multiple ways of using the Google Cloud without sort of having to have a bunch of funding to make it work.
Thanks.
Anybody else have any questions? Okay, well.
Fabian, I was just going to add, this is Cawthor. Fabian just showed that we've made the scripts and a handout available in the presentation drive that Mo, you created. And if anyone's interested in working along, basically replicating what Fabian just showed, if you share with us your email addresses, I don't know, Fabian, if you could bring up the slide with our email addresses, we can add you to the project we created, and you then have access to the Google Cloud platform, the AI platform, to be able to run and basically follow along.
Was there any more that you guys wanted to show from ISB CGC side, CRDC?
No, that was pretty much it. I mean, we wanted to show a high level analysis and then let people kind of work on the stuff themselves. So we've made like a handout available that basically step by step goes through what Fabian just showed and then the actual scripts that he was using. And again, just if you want to email us to be added to the project, so that you'll have access to the project to be able to run those queries. And we'll make it available for about you can run stuff for about 3 to 4 days.
From the CRDC perspective, this is David Pott from ISB CGC. Certainly, there are the other 2 cloud resources that you've heard a lot with, Terra, which is called FireCloud in CRDC, as well as 7 Bridges. So we're very actively collaborating with them and trying to do handoffs and such. As well as the University of Chicago and the Data Commons framework. So a lot of interaction there. I think that CRDC approaches it from various users can choose the platform they're interested in based on their workflows, based on their expertise, based on if they're working on various data sets, that sort of thing. I don't know if that answers the question that you might have had, Mo.
I think one of the real benefits too is that you can access Google BigQuery through a whole bunch of different interfaces. There's a Python library, there's an R library, there's the command line interface too, just a bash interface. So it should be possible as long as you have a Google login to access these tables and for your users to access these tables from any sort of interface that they may be choosing, or that they may want to use.
Are there any additional questions or comments? All right, well, that brings us to the end of the use cases for today. I'd like to make a couple quick points for follow-up. The April 16th workshop for interoperability has also been converted to a remote event. I think everybody should have gotten an email. If you did not get an email, feel free to contact myself or Rich Silva. Another thing to follow up on are the working groups that we have established for these interoperability efforts. So as we heard at the beginning of yesterday's sessions, we have the Systems Interoperability Working Group that is approaching interoperability from a development side and using a number of well fleshed out use cases to add components and further develop our platforms to be able to work together. The other interoperability working group that we've been focusing on a lot, and we have opportunities for follow-up, is the Outreach Working Group. Feel free to contact myself if you'd like to learn more, but in short, we're trying to educate our user bases about our platforms and tackle challenging problems that we all face. So managing cloud costs is at the top of our list, and based on our discussion earlier, I think developing better and unrestricted training data sets are a priority for us. I'd encourage everybody to get as involved as possible with these interoperability efforts because it ultimately benefits the user, and the user may be the one that saves all of us from coronavirus. So let's continue to support these people. I would like to really give a huge thank you to all of the presenters and speakers. What you all did over the past 2 days is very challenging, and you all are kind of writing the book on how to do these remote type events. So I'll encourage everybody to unmute themselves and give you a round of applause.
Thank you again, Mo, for all the organization.
My pleasure. We'll follow up with links to the documents. I'll also include a feedback form so we can learn from this event to make future remote events as good as this one. And I'd also remind folks to sign up for the virtual Q&As this evening. A bunch of us were in them last night, and it was nice to interact and talk to people again. So please feel free to join. Hopefully we find a way to continue these virtual Q&As so that we don't all lose our minds in isolation. I'll thank everybody again for their time over these past 2 days, and I look forward to seeing everybody virtually. Bye-bye.
Bye.
Thanks, Mal. Bye-bye.
Bye. Thank you.
Bye.
Bye.
Thank you.
Bye.
Bye.
Bye all.